Good morning. So, welcome to the third lecture on modulation, and last time when we finished our lecture we finished with these 3 points that we would like to do today. First we would think about how can we design a passband filter in baseband domain, that is the first idea that we would explore. The second thing that we would do is we would understand these frequency offset and phase offset effects, and we would see how can we get rid of them in baseband domain, okay, in baseband processing. The third thing that we would do is we would like to think about the coherent receivers and non-coherent receivers. We have the entire unit on receivers, so that would happen after modulation. So, here we would just talk about some ideas, just getting started with receivers. So, let us take the first problem head on, and that problem is that if I have a passband signal SPT, and this passband signal I want to pass it through a filter which is a passband filter HPT, and what I get is YPT, which is a passband signal. Now, I do not want to design this filter in passband domain, right. Designing this would involve making analog demodulators or modulators, and this would be complicated, right, and we would like to do everything in baseband domain. So, we would like also to make this filter in the baseband domain, and today we will see how can we do that. So, the idea is equivalent filter in baseband. Okay. So, implementing a passband filter in baseband. So, if we look at this, you know from basic again the course in signals and systems, that the spectrum output is spectrum by YPF is nothing but it is the spectrum of this filter. Let me call this as HPF, and let us say that the spectrum of this signal SPT is SPF, right. So, this is true in general if this filter is an LTI filter, which we have assumed that this is a linear time invariant filter, then I can write this YPF is the product of the filter response and the signals spectrum. This is very basic. Okay. Now, we also know, because we have derived an equivalence between the frequency response of the baseband signal and the passband frequency response. So, for example, we have said that SF would be nothing but it would be root 2 times SP plus F plus FC. This is a relationship that we derived in the last lecture, and similarly HF can be written as root 2 times HP plus F plus FC. Finally, what we would get is YF would be root 2 times YP plus F plus FC. Okay. Now, so we know that YPF is HPF times SPF. So, from this we can see that YP plus F plus FC would be HP plus F plus FC times SP plus F plus FC. And now, using the equivalence between the spectrum of a baseband signal and a passband signal, I can write this as YF by root 2, this is HF by root 2, this is SF by root 2. So, what I end up with is YF is HF SF divided by root 2. So, what we learn from this is, if you have a baseband signal, two baseband signals, you can do this operation in a baseband domain. What you end up with is the spectrum of the resultant baseband signal, right. So, YF is the spectrum of the baseband signal of YPT. Okay. Let us see more about this. So, HF we can write that this is nothing but this would be the spectrum of HCF plus HSF. So, remember that a signal, when we are talking about the baseband signal, it is composed of the two parts, cosine parts and the sine part, and the spectrum of this HF would be nothing but the spectrum of the cosine part and the spectrum of the sine part. Similarly, SF I can write as SCF plus J times SSF. If I want to multiply these two things, for simplicity again I ignore this F, what I would have is HC plus JHS multiplied by SC plus JSS. I have omitted the F part and then I multiply. So, this would be HC minus HSSS. So, plugging in the real parts plus J times HSSC, then I would have a term from there which is HCSS. So, what this means is I can take SC, you can start with HC, I multiply this HC with HC. Let me take a filter whose impulse response is HCT. Okay. So, let me have SS multiplied by HS and then I add these two parts, this I add with positive, this I add with negative, and what I get is the root 2 times YC T, if you like, you can put T everywhere. So, what I am saying, if you look at this expression, this would give me the cosine part of YT. Okay. This, when I multiply HF with SF, I get YF. So, when I do this, this corresponds to the spectrum of the cosine part of YF, right. So, its inverse transform is YCT. Now, you may wonder that here I have been talking about the spectrum and here we are writing with the impulse response, and the reason is very simple. So, if you look at this, the output is HCF into HCF. So, once you want to multiply HC with HC where these correspond to the spectrum, this is exactly what we are doing, right. So, when you multiply the spectrum, what you need to do is you just have to pass the signal through a system whose impulse response is the inverse Fourier transform of HCF, and you get the resultant spectrum at this point. So, this would give me root 2 YCT. Similarly, what I can do is now I have to make this part. So, I have to multiply SC with HS. So, let me do this, and I have to multiply SS with HC, add these two things up, what I get is root 2 times YST. Okay. So, basically what I do is I start with the baseband signal. If I have baseband signal, and in this baseband signal what I do is I pass these baseband signals, the cosine and sine parts of this baseband signal through this filter. This filter is completely in baseband domain. All these things, all these impulse response are corresponding to baseband signals. What I end up with is the sine and cosine part of yt, and this sine and cosine part of this yt would correspond to a system, to a passband system with which we have started with, which would have been implemented like this. So, instead of implementing this filter HPT in passband domain, we can implement this filter in the baseband domain. Okay. So, that gives us some idea about what we have to do in baseband and how can we implement some of the filters of the passband in baseband. Let us now look at another interesting problem of frequency and phase offsets. Second important example that deals with frequency and phase offsets. So, let us look at this picture that we have seen several times, which says that if you have SPT, you pass it through Hilbert filter, you multiply this thing with root 2 e to the power minus j omega c t, and we have said you get ST. And if you have noticed that this rotating complex exponential should be compliant or should be synchronized to the rotating complex exponential that you used at the transmitter. So, at this transmitter, remember that we had ST which was multiplied by root 2 e to the power j omega c t, then we pass it through a system which takes the real part and it was giving us SPT. So, this was at the transmitter and this is at the receiver. Now, if this e to the power j omega c t and this e to the power minus j omega c t does not have same frequencies, for example, then what you would end up with is a different signal, you would not recover ST. Okay. So, when I say that I can recover ST, I assume that I have a signal available which has a frequency omega c and it is matched to the frequency of the modulator that I was using at the transmitter. In general, that is not the case, because this modulator and this modulator or demodulator are at different locations, and normally they would have some frequency differences. Okay, so, we are trying to investigate now the situation in which the frequency of this carrier is different from the frequency of this carrier. So, let us now assume that we have a situation in which we have SPT, we pass it through a Hilbert filter, that is good, but at this multiplier what we have is e to the power minus j omega c t minus theta t. Okay. So, this theta t would take care of any differences in the frequency and phase of this carrier with respect to the carrier that we used at the transmitter. And if you do some maths, you can quickly see that the output that we will get in this case is ST e to the power j theta t. Okay. So, what we are getting is not ST, but ST multiplied by this complex exponential. Okay. Let us see what can be a typical example of theta t. Let us take theta t to be 2 pi a t plus b. So, the phase varies linearly with time and there is some initialization value, right. So, when you put t equal to 0, then you have b, otherwise the phase varies linearly with time. Okay. Now, if you look at this expression, if I want to find what is the frequency deviation, what frequency deviation this would create. So, the frequency deviation, of course, angular frequency deviation would be d theta t dt, which in this case would be 2 pi a. If I am interested in the frequency deviation in hertz, this is in radian per second, I would get A. So, this A constant corresponds to the frequency deviation or frequency offset. So, A corresponds to frequency offsets and B corresponds to the phase offset. So, now because of this theta t, the phase of the carrier is different from the carrier which I used at the transmitter, and also the frequency of the carrier is different, and one simple expression like this captures both these effects. Okay. Now, let us see what happens because of these phase and frequency offsets. So, what I am receiving is ST, let me call as ST tilde, because I am receiving something different from actually what was transmitted, is ST e to the power j theta t. I can write this as SCT plus j SST times cos theta t plus j sin theta t, and I can write this as SC tilde t plus j SST tilde. It is different from what was transmitted. So, in one go without any difficulty you can write that SC tilde is SC cos theta. I am omitting t for again for typographical reasons. So, I need to multiply this with this, and I can multiply this with this, and SS tilde would be SS cos theta, then I would have SC sin theta. Now, so we end up with is we are receiving something different from what was transmitted. We transmitted SC and SS, sine and cosine parts, right, but we are receiving a different sine and cosine parts. Now, how to deal with this situation? When you want to deal with this situation, what you do is you assume some synchronization at the receiver. So, synchronization can mean different things depending upon the context. Here what I mean is the transmitter can solve this problem. He can transmit a known value of cosine and sine part of the signal. So, he can transmit the known value of SC and SS in certain duration. So, receiver knows when he is receiving the known value of SC and SS. So, when the receiver receives SC and SS tilde instead of SC and SS, but he was expecting SC and SS. So, what he knows is this and this, and what is receiving this and this. So, based on this what he can do is he can calculate theta, okay, and he can adjust the phase and the frequency of the carrier by knowing this value of theta. That is one way. The second way, and the way it is done, is that instead of shifting the frequency and phase of the carrier, it is difficult to do. You take care of this effect in the baseband domain. So, you do not touch your carrier that you are using at the receiver, but rather you are taking care of this effect at the signal processing level, at the baseband level, at the computer level. Okay. So, let us try to see how can we get rid of this at the baseband level. So, let me multiply SC tilde with cos theta. I get SC cos square theta minus SS sin theta cos theta. That let us say equation number 1. I can multiply SS tilde with sin theta. I get SS cos theta sin theta plus SC sin square theta. Let us say equation number 2. I can add these two equations. I get SC tilde cos theta plus SS tilde sin theta, and while adding these two up, this term will disappear. What you end up with is SC. So, based on what you are receiving different cosine and sine part. You already know what the value of theta is. You have obtained this by doing some process of synchronization. The process of synchronization is simple. Receiver knows what that is expected to get, transmitter sends the same signal in the desired period, and based on the received signal it is anticipating the distortion and it can correct this as it would do now. So, we know that after the phase of synchronization this value of theta has been obtained at the receiver. Now, I have solved for SC, and if I want to solve for SS, this would be simple. You can work this out. This would be SC tilde cos theta with a minus, sorry. So, you can work out the value of SS yourself from these two equations. So, when we want SS, it would be minus SC tilde sin theta plus SS tilde cos theta. So, using these two equations you can easily derive these two equations. Okay. So, we can find out the value of SC and SS, the desired values of SC and SS from the received values of SC and SS and from the known value of theta. How would the receiver structure look like? So, receiver structure, you can use these two expressions. So, you take SC tilde, whatever you are receiving, you multiply this SC tilde with cos theta, and you take SS tilde, you multiply this with sin theta, you add these two things up, what you get is SC. What you can do then is you take SC tilde, you multiply this with minus sin theta, you take this, multiply this with cos theta, and you add these two things up, what you get is SS. So, this is a kind of structure that you need to use to obtain the desired values of SC and SS from SC tilde and SS tilde by compensating the values of frequency and phase offset. So, this you can implement at baseband domain without touching up your carrier which was working at the passband. So, we have seen two interesting problems. We are just trying to motivate you that certain complicated operations at the passband can be done fairly easily at the baseband. I am saying fairly easily because processing comes at no cost, right. Digital signal processing has become very cheap, right. So, you are just changing or manipulating some numbers in a signal processor. So, that is almost no cost. So, all these complications that we had to deal with in analog domain before, now all these problems can be easily transported to baseband domain, right, and this is how most of the things are being handled today. The third important point that we would like to talk about is coherent and non-coherent receivers. And as I have said, we will like to talk about these coherent and non-coherent receivers in great detail later on, but at this point it is really instructive to get some flavor of what are these coherent and non-coherent receivers. So, the idea is very simple. So, what we are saying is we are receiving, let us say we are receiving some ASP plus NP. So, this is a passband signal. So, we are receiving something that was transmitted, that is SP, we have multiplied it with some constant A, and to this what we add is a noise. As you can see that noise adds to the signal. So, this is a signal and this is the noise. So, what you would receive is signal plus noise. Noise is adding to the signal and hence this is known as additive noise, right. If noise would have multiplied with the signal, we would have called it as multiplicative noise, but noise normally we assume to be additive and not to be multiplicative. Also, we have seen in the lectures in the noise that the noise is white Gaussian noise, that is the noise that we like to use for modeling the physical noise processes, and hence this is also known as additive white Gaussian noise. Anyway, at this point I am just trying to introduce you to a model in which we are using a signal and we have some noise addition, and this is what you are receiving. Now, in digital communication we normally have a set of signals right. For example, let me take just two signals. So, let me assume that I have a binary set. So, I have two waveforms that I can transmit, either I can transmit S1T or I can transmit S2T, and at the receiver my job would be to identify which waveform I have transmitted, whether I have transmitted S1T or S2T. So, this is the job of the receiver. So, what receiver does is whatever it receives, it takes the inner product with this. Okay. So, let us say it receives YP and it takes the inner product with a signal S1. It receives YP and it takes the inner product with signal S2. So, this is normally what a receiver does. Okay. So, let me assume a very simple case that whatever I am receiving, let us assume it to be ASP plus NP, and let us, without worrying about whether that is an optimal thing to do or not, let us just take the inner product of YP and SP, because SP was transmitted, and let us see if the receiver does the inner product with the signal that was transmitted, what do we get. Okay. So, this is ASP plus NP with SP. Of course, because we have been talking about a lot of baseband, you know that this inner product would be calculated in the baseband domain and not in passband domain. So, how would we do it in baseband? So, this is nothing but you have to take real part of AS plus N and S, okay, where S represents the complex baseband equivalent of the passband signal. Now, if you do this, what you get is, let us now assume noise to be 0. Okay. So, let me put it to 0 for simplicity. What do we get is real part of A S with S, and this is nothing but A norm S square, right. This we have already seen. So, now what you get at the receiver is A times energy of SP. So, at the receiver you would see that most of the detection happens based on the energy of the received signal. So, this looks fairly okay. Now, let us see what happens if I have a non-coherent receiver instead of a coherent receiver. So, what would change? The thing that would change is, instead of having AS in non-coherent receiver, what we would have is AS e to the power j theta plus N and S. Why do we have this e to the power j theta? Because the basic difference between coherent and non-coherent receiver is that we assume that the coherent receiver has the complete information about the frequency and phase of the carrier used at the transmitter, or it can synchronize itself to the phase and frequency of the carrier, or it can use a structure like this to get rid of this frequency and phase offset. So, there are no errors introduced because of a mismatch in the frequency and phase of the carrier used at the receiver and the frequency and phase of the carrier used at the transmitter. So, a coherent receiver would employ a structure like this, and when it employs a structure like this, and the coherent receiver, we can assume that we are having AS instead of A as e to the power j theta, because that part has been taken care of. In non-coherent receiver, what we normally assume is that non-coherent receiver does not use such a complicated structure. It simplifies the design by not using it, but then it has to pay some penalty, right, and this penalty we will see when we will talk about the performance of non-coherent receivers. At this point, let us just see what happens if you do or you compute this inner product for a non-coherent receiver. Of course, we need to have the real part as before. So, if you do this, again we can assume noise is 0, noise is no problem, because we have not discussed the interaction of noise and so on and so forth with the signals. We will do this in receiver. I do not want to bring in that complexity. Safely I am assuming that there is no noise. So, what this inner product operation boils down to is real part of inner product of A s e to the power j theta and s. So, if you do this, what you get is a norm of s square cos theta. And now there is a trouble, because theta can be anything, right, and if I assume theta to be 90 degree, cos theta is 0, that means this quantity goes down to 0. That means even if there is no noise in the receiver, because I am using a non-coherent receiver, I can get a flat 0, and getting a flat 0 means I would have a lot of errors and this design is not going to work. So, when you are having a non-coherent receiver, it is not a good idea to take the real part of these complex baseband signals. Instead, what you should do is you should take, so in non-coherent receivers, what should we do is we should take the magnitude, and that is important, we should take the magnitude of this inner product. Once you do this, it is easy. If you take the magnitude of A e j theta s with s, what you would get is, this is a constant, it can be pulled out, taking the magnitude of this would be 1. So, what we end up with is a norm s square, same as what we got in the case of the coherent receivers. So, this is little bit misleading, because we are claiming that the performance of non-coherent receivers is same as the coherent receiver. That is not the case. This has turned out to be the same, because we have not taken into account the nonlinear interaction of noise with signal that happens in the non-coherent receivers. We will talk about all these issues when we discuss about the non-coherent receivers. At this point, the main message is that whether you should take the real part of the inner product or whether you should take the magnitude of the inner product depends upon the receiver design, and both these operations are used. We take the real part of the inner product of the complex baseband signals when we are doing, or we are in the regime of coherent receivers, and we have to take the magnitude of the inner product of the complex baseband signals when we are talking about the non-coherent receivers. Okay, so with this we have completed our discussion on the relationships between the complex baseband and passband signals, and this is really an important equivalence that you should understand, because the approach that we would take in this course is we will only talk about the modulation and demodulation in the baseband domain. We would not talk about the modulation and demodulation in the passband domain, though there are certain books which attempt it. We would not do that, because once we have understood everything about the baseband modulation and demodulation, and once we have understood the equivalence between passband and baseband, that exercise is little bit trivial and redundant. So, what we have done and we have emphasized upon this equivalence is also because of this reason, because we will not discuss the passband modulation and demodulation schemes, and that is also the case, means all this modulation and demodulation happens at the baseband only in the practical communication systems, and what you then do is you just multiply it with this carrier and you go to the passband domain, and from the passband you also come back to baseband domain by using this passband to baseband converter. Okay. So, let us see what we have discussed so far. So, up to now we have clearly understood the relationship between this baseband signal and this passband signal, and now from today onwards we will be trying to investigate what happens when you convert a binary sequence to these samples and how is the modulator impacted by the impulse response of this filter. So, first thing that we will start investigating today is the influence of this AKs and this PT on the bandwidth occupancy of the modulation scheme. That means, how you choose the weights for this binary sequence and how do you choose the impulse response of the filter. One of the important parameter in digital communication system is the bandwidth occupancy of the modulation scheme, because the operators have to pay for that, right. So, what we want to do is we have to minimize, or we want to minimize the bandwidth requirement for the given transmission of information. And we will see that the bandwidth occupancy is a very strong function of how you choose this AKs and how you choose this PT. Okay. So, this is what we are up to in this lecture and over next couple of lectures to study about the spectral description of sources. Remember that the binary sequence that is available to this modulator is a random sequence and it is a stationary sequence. So, the idea is that you simply take the Fourier transform of this to get the spectrum, and the bandwidth occupancy of the signal will not be useful, because as we will see that this sequence, if it is a stationary, might have infinite energy, and thus we cannot take the Fourier transform of this random stationary sequence easily, and thus we have to do something else to evaluate the spectral description of this random source. So, we would be using the ideas that we developed in random processes. We will be thinking about autocorrelation function and so on and so forth. So, this is exactly what we are up for in this second unit that we have started in modulation, trying to study about the effect of AKs and PT on a spectral description of sources. One more point that you have to be careful in the use of definitions again. So, if you have this binary sequence, whatever this binary sequence is, as we have already said that the first step is to go from this bits to samples. So, at this point we have a weighted train of impulses, and then from this weighted train of impulse, when you pass this through a filter with impulse response PT, you get an analog waveform, and as I have said that this is a baseband waveform, and we have already said that we can study everything in baseband domain without going to passband, because you can go back and forth between baseband and passband without losing out information, and this conversion is straightforward and easy. Thus, if we confine ourselves to the discussion in the baseband domain, it would be sufficient. Converting a baseband signal to passband signal has already been covered by us, and thus we will confine ourselves in rest of the modulation that we discuss to baseband signals. We would stop ourselves at this point, okay, because this to this has been understood. Thus, we will study about modulation only in baseband domain from now onwards. And the second point is that if you have a baseband signal available at the output of the modulator, so modulation is referred to as line coding, because now the job of a modulator is just to produce the waveforms which are suitable for baseband channels. So, modulator is same thing as a line coder, if we are just confining ourselves to this step. Okay. So, instead of saying that you have a modulator, we can also say this as a line coder. So, what is a line coder? It just have two elements. First, there is a bits to sample converter and then there is a filter, okay, and this is a line coder. It produces baseband analog waveforms which are suitable for transmission over baseband channels. So, line coder is a part of a modulator. Okay. So, sometimes we also call this as line coding schemes. Okay. So, next thing that we will do is to talk about spectral description of sources, and the big idea in this topic is we would like to see what is the bandwidth occupancy of my waveforms. And this is bandwidth is a really important thing, because bandwidth comes at a price and you want to minimize the bandwidth occupancy of your waveforms. So, let us start with a source. Let us say that the waveform, the baseband waveform that I have is summation B n P t minus n t, and going from minus infinity to plus infinity. Let me explain this from where we get this expression, though we have discussed it several times, but it will be really nice that I revise this for you. And what happens actually is that you have some binary sequence available, you map these binary sequence in numbers. So, I map this, let us say, to some number a 0, this a 1, a 2 and so on and so forth. I map these logical sequence to some numbers, some electrical voltages, then I create an impulse train, and the weights of this impulse train is decided by these numbers. So, what you have is summation a k delta t minus k t. So, you take a binary sequence, you find some real numbers corresponding to a sequence, you create an impulse train, weights of the impulse train is decided by these numbers, then you create an impulse train. This is an impulse train, impulse located at 0, t, 2t, 3t, and the weights of the impulse is given by AKs. Now, then you pass this impulse train through a filter. So, passing through a filter, that means I need to convolve this with the impulse response of the filter. Let us assume that the impulse response of the filter is p t. So, what you get is k going from minus infinity to plus infinity a k p t minus k t. As I have said, these are typical steps that happen at the modulator. Not all modulators can be described using these simple steps. So, now let us go back to the equation that I have written. So, I have written S t is summation B n P t minus n t, either you use n or k, does not matter, and going from minus infinity to plus infinity. Now, if you see this equation, this is an example of what we call as linear modulation. Linear modulation means that the pulse that you are using is common. So, all real numbers or all numbers are modulated using the same pulse. In fact, we are just concentrating on real numbers, but this can be complex as well. So, this Bn can be complex. Let us generalize this to complex. So, if this is complex, what I have is Brn Pt minus Nt n minus infinity to plus infinity plus j times B Cn Pt minus Nt. and then you can consider this as ST, the complex baseband waveform. Okay. So, it is a simple. So, this would then denote this is all analytical SCT and this is SST for example. Okay. So, we can assume these numbers to be complex numbers, and if we assume these numbers to be complex number, you see that this is actually ST, this is a complex waveform, assuming that this is real. If this is complex, this is real, you will eventually get a complex thing, and so this will be a complex baseband waveform. It can be decomposed into two real waveforms. So, one you can treat as SST, SCT, and the other one you can treat as ST. Okay. So, eventually you can assume Bn to be real as well as complex. Now, anyway, let us not digress to this whether it is real or complex. Let us keep focus on the point that I mentioned before, that we are treating, we will be treating this, or this is treated as a linear modulation. You are using the same pulse shapes, okay, for all numbers. So, do not understand that linear modulation is only the kind of modulation. We also have non-linear modulation, okay, in which you have different pulses to transmit different signals. This is linear modulation, and for some time we would just focus on linear modulation. Okay. So, we are trying to start with this expression, but there are so many things that we want to say about this simple expression. Again, we will revise what are the important things that we have said. We have said that this is an example of a linear modulation because we are using the same pulse for transmitting all real numbers. Then we have said that this Bn can be complex. In that case, ST would be a complex baseband waveform, and you can understand this to be composed of two real baseband waveforms. Okay. Now, let us try to define the power spectral density of this sequence. To find out the power spectral density, the first thing that we need to do is to find out the Fourier transform. So, let us try to find the Fourier transform of ST, which I call as SF. Now, if you want to find the Fourier transform of this sequence, you would end up in trouble, and the reason is because this Bn goes from minus infinity to plus infinity. So, the energy of this sequence would be infinite. Okay. If I assume that this sequence is stationary, for example, if I assume this Bn to be stationary, that means Bn should be defined from n going from minus infinity to plus infinity, then what would happen is that the energy would definitely be infinite with probability 1, and in that case the Fourier transform may not be defined, right. So, when we are trying to find out the Fourier transform of this expression, it would not be possible, right. So, rather than finding the Fourier transform of this expression, we modify our equation. So, we say that we are not having ST going from minus infinity to plus infinity, rather we have truncated it to T naught. So, let us say we are using ST and I have truncated it for a duration T. So, now what I am saying is I am having a signal which spans only from minus T naught by 2 to plus T naught by 2. If I am truncating a signal for a finite duration, the energy of that signal will also be finite. So, this allows that now we can calculate the Fourier transform of this signal. Okay. So, Fourier transform of this signal can easily be calculated, which I say ST naught f, it is the Fourier transform of ST naught t. Okay. Now, if I define the energy spectral density of this signal is nothing but ST naught f mod square. Let us see why this is energy spectral density, because you know from basics that the energy of the signal is this, and again from Parsible's theorem you can think about the energy as this, and if this is the energy, this quantity will be energy spectral density, because you need to take energy spectral density integrated for a band of frequencies, and then you get the energy. So, this quantity is thus energy spectral density. So, energy spectral density of S T naught T would be this. What would be its power spectral density? Power spectral density is nothing but it is the energy spectral density by the time duration, right, and the time duration of the signal is T naught. So, power spectral density is mod S T naught F square divided by T naught, right, and because we do not have the good notation, we would denote power spectral density with Z of f, right. We earlier have used S of f, but now S of f is we are using for the spectrum of a signal S T. So, let us use Z of f to denote the power spectral density. Now, this is the power spectral density for a signal which runs for a duration of T naught. Now, I can probably calculate this quantity by taking the limit of T naught to infinity, and this is how you define the power spectral density of S T naught T. First you truncate the signal for a duration of T naught, so that the energy of the signal is finite, so that the Fourier transform is defined, otherwise you cannot take the Fourier transform of the signal which has infinite energy, and then you divide it by T naught, and then you take the limit of T naught to infinity. So, now we have derived just basic expression of how can we calculate the power spectral density of a signal, and we will work upon these equations. We will develop some interesting equations of the power spectral density of certain waveforms, and we will see that certain waveforms occupy more bandwidth than the other waveforms. So, there is a lot of interesting things to happen in the next lecture. See you.